Hi everyone, in this video we're going to use the envelope detector circuit that we built in the previous video to measure the envelope of three different amplitude modulated signals. Now for two of these measurements, the modulating signal is going to be a shifted sinusoid at a low frequency, and for the other measurement, our modulating signal is going to be a shifted triangle wave, also at a low frequency. So to do this, let's first head over to the Waveforms app. We're going to use the Waveform Generator to generate our amplitude modulated waveforms, so click WaveGen. Now it turns out that we can't use a simple waveform configuration to build our amplitude modulated signal. So in order to do that, click this drop down menu and select the waveform type called modulation. And so as you can see, this allows us to build signals that have both frequency modulation and amplitude modulation. Now, since in this lab we're only dealing with amplitude modulation and not frequency modulation, deselect the FM checkbox, so we're only generating an amplitude modulated signal. So now let's specify the parameters for the carrier and the modulating signal. So our carrier for the first measurement is going to have a frequency of 1 kilohertz. The amplitude is going to be set to 2 volts, and the offset, symmetry, and phase can all be left the same. Now head over to the AM column. This is where we specify parameters about the modulating signal. The frequency is going to be 10 Hertz. Now this field here, this is where we specify the modulation depth of our amplitude modulated signal. Now if we call the modulating signal x of t, then the modulation depth is defined as the maximum of x of t minus the minimum of x of t divided by 2 times the amplitude. So we want the maximum of our modulating signal to be 3 volts, the minimum to be 1 volt, and our amplitude is 2 volts. So therefore the modulation depth is 3 minus 1, which is 2, over 2 times the amplitude, which is 2. And that evaluates to 50%. So in this index field here, enter in the modulation depth, which is 50%. So we've specified the necessary parameters in order to generate our amplitude modulated waveform. Now press run, and this will actually send the amplitude modulated waveform through the WaveGen into our circuit. The last thing we have to do before we can view our output is that we need to power our op amp with plus or minus 5 volts. So to do that, head over to the supplies application and then change the positive power supply to 5 volts and the negative power supply to minus 5 volts. And then click this button. It should read master enable is on. This means that both the positive power supply and the negative power supply have been enabled and they're set to plus or minus 5 volts. And so with that, we can head over to our oscilloscope and view our output. Now I'm going to change a few of these parameters here. We're going to use a time division of 100 milliseconds per division. The ranges for channel 1 and channel 2 are both going to be 1 volts per division. And now I'm going to set the trigger to use a normal repeated mode. The source is going to be channel 1, and we're going to use a rising condition. And so with that, I'm going to press single to perform a single acquisition of our output. And when I press single, we can see that the yellow waveform is our input signal, which is an amplitude modulated waveform. And then this blue signal is our output waveform. Now you might wonder why the blue waveform is shifted by around 0.5 volts relative to the actual envelope. And this is due to the fact that the diode, the PN junction diode, has a forward voltage of around 0.5 or 0.6 volts. This is why this envelope comes as the 0.5 volts lower than the actual envelope. Now just to make the graph a little neater, we can shift this up by 0.5 volts or so that it appears as if it's actually the envelope. Besides the forward voltage of the diode, our envelope detector is very accurately detecting the envelope of our amplitude modulated signal. We can zoom in a little bit, change the time division to 50 milliseconds per division. Now we can see a little closer up view. As you can see, when the modulating signal is both increasing and decreasing, our envelope detector can reasonably follow the envelope and produce this sort of waveform. This is exactly what we want our envelope detector to look like. So since we're happy with the output, let's head over to export and then under the Image tab, press Save to save an image of your output. Now I'm going to perform the second measurement, and which the second measurement is pretty much identical to the first measurement, except the carrier frequency is going to be 200 Hz as opposed to 1 kHz. And so I'll let you do that measurement. Lastly, the third measurement is we're going to use a carrier frequency of 1 kHz, but instead of using a sine wave as our modulating signal, I'm going to use a triangle wave. So change the type from sine to triangle, and we're still going to have a modulation depth of 50%, and our frequency is still 10 Hz. So with that, head back over to our oscilloscope. I'm going to change this back to 100 milliseconds per division, and I'll press single to perform a single acquisition of our output. And so this is the output of our envelope detector when our input is an amplitude modulated signal, where the modulating signal is a triangle wave at a low frequency of 10 Hz. And so if I zoom in a little bit, I change the time axis to 15 milliseconds per division. We can see that our envelope detector is very reasonably following our envelope. And so since this is exactly what we expect based off of theory, let's head over to Export, and let's save the image by going to the Image tab and then pressing Save. Alright, so this is it for section 2 of the lab. And so in the next video, I'm going to summarize the key takeaway points from the lab, and I'll also briefly talk about what you'll be asked to do in the post lab.